Welcome to the Math Record. Today we'll be covering Taylor and Maclaurin series. This video will cover part 5 of chapter 4, which is also the final video for our calculus class. Okay, let's begin. So what is a Taylor series and what is a Maclaurin series? Basically, a Taylor and Maclaurin series is used to rewrite non-polynomial equations into polynomials. So, for example, let's say we have a non-polynomial. Let's say sine of x, right? So we have a trig function, something like this, right? Ish. I'll draw this side too. Not the best artist live. Okay, so something like this, ish. Sorry about the bad design. But basically we have a sine of x, right? So instead of having sine of x as a trig function, how do we write sine of x as a polynomial? Well, let's think about this as smaller parts. Let's think about this as a linear first, right? So this is when n is equal to 1, right? When it's degree 1. So this is the first degree. So does a linear look like a sine function? Well, no, right? Because a sine function have a bunch of these curves, while a linear is just a straight line. So that doesn't look that precise. But it's a good place to start from, but it's not really that precise. So let's kind of think about this as a quadratic now, right? So we have something like this. Does this look like a sine of x now? Well, if you think about it, we have n is equal to 2 as a quadratic, right? We have a curve, right? A quadratic is a curve. And now it's even more closer and it's more precise because now we could just, let's kind of like not look at this section, look at this section right here, right? It kind of looks like this section, right? Doesn't it? And that's the idea of like using more polynomials to like make it more precise. Oops, sorry about that. Now let's kind of expand that even further. Now let's use a cubic. So we have something like this, right? Which now even makes more sense, right? Because we have this negative section, which is just like this section. We have this positive section, like this section, right? So it's getting even more precise. Now let's kind of use a quatric, okay? Where n is equal to 4, right? So we have something like, I don't know, like something like this-ish. Oops. Actually, yeah, something like this. They're not, I might have moved the graph a little bit, but basically I'm just trying to use it as an idea to show. Right? So this is like a general idea of a quatric. It kind of looks like a W-ish if you ever looked at quatric equation before. Right? We have this part right here, this really small part, which looks like this part. And then we have it increasing, right? Like this. We have this small hump, right? Which is like this hump. We have this hump right here, which is like this hump. And it's increasing at this section, like this one. So what I'm trying to get by using these equations is to show that as we increase the degrees, right, we increase the amount of terms in our polynomial, we get precise and even more precise like polynomials to represent non-polynomial equations. So while we started something with like a linear, we went from a quadratic to a cubic to a quatric. And if we use n to the power of n equals 5, n equals 6, n equals 7, n equals 8, right, etc., we add more, we get an even more precise polynomial to represent a sine chart, a sine graph. Because instead of like writing equations that are non-polynomial, like exponentials, logs, trig, right? Instead of writing it exactly as a like their specific functions, we could convert them all into polynomials, which is easier to understand. So how do we do that though? We've been explaining how this works, but how do we do it? Well, basically, we already made a general formula how this works. It's basically a summation, right, from n equals 0. So we start from a first degree, right, which makes sense. And then there's infinity, right? Because we want to add an infinite amount of terms. That's the idea of calculus. So we have f of n to power 0. I mean f of n, not power 0. Actually, sorry, not 0. Of a. And then we have n factorial times x minus a to the power of n. So n is our degrees, right? So this thing just gonna represent where our the terms of our polynomial. And this section is gonna get us the coefficient. Okay? So the reason we divide by n factorial is that we want to add small changes, not really big, right? Because imagine if the derivative, this section, which calculates for derivative, is increasing, then basically, then n factorial is supposed to limit that. So we want to make it smaller and smaller and smaller because we don't want the polynomial to be increasing every single time, right? Because for example, let's say we have like 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the power 4, right? That doesn't make sense, right? Because if we graph this out, it's going to be really, really imprecise, right? Because if we want to use that to represent a sine graph, right? So something like this, etc. If we have this graph, we have something like um, this, right? Actually, that's kind of a bad diagram. So let's kind of rewrite this. So we have something like a small and then a really, really big change, right? Because we started at small, but then as you increase the amount of x, as x increases, right, we have really, really big changes, which doesn't make sense because as we increase, it's alternating between these waves. So the reason we have this n factorial is that we had to limit it. So instead of something that looks like this, we have to have it something like 1 plus 1 half x plus 1 third x squared plus 1/4 x cubed plus 1/5 x to the power 4. So now the graph kind of looks something like, right, we have a power of 4. So now we have something like really, really small changes, right? So it looks something like this, which is better because later on, if we add more and more terms, this graph would kind of get even more precise. So it kind of looks like this, right? It gets smaller and smaller, right? So it gets like better changes overall. So that might be a little bit too extreme, why it might be a little confusing to understand. So, so that, let's say something like this, right? And then later on, as we add more and more terms, we have something like this, right? It's getting smaller, right? But as we add more terms later on, we're also increasing the humps, right? Because we're accounting for even smaller changes in the y value. And that's the idea of the Taylor series. Okay, let's kind of delete this section. So this is just for the Taylor series. So what is a Maclaurin series then? Well, a Maclaurin series is a specific Taylor series. A Maclaurin is basically A when A is equal to 0. So the reason we have A here, A is basically the center of our graph. So let's say we have a Taylor series centered right at the origin, right? That's going to be a Maclaurin. Any Taylor center at a origin is going to be a Maclaurin, right? So this is when A is equal to 0, right? So when the graph is centered at 0. But imagine that the equation that we want, like, is right here, right? It's centered at A is equal to -1, right? This point right here is -1, 0. So instead of like having a Taylor that looks exactly like it but at different places, we could shift that Taylor series to make it to like over here, right? Sorry, oops, I don't know why I draw an arrow there. We could shift this Taylor series over to the left and make it into this equation, right? So we move this entire equation to the left by 1. So we move this point right here, move all these points over, and then we could just get like a straight line for our Taylor series, right? So now our new equation is like over here, which matches this equation, which matches that graph, right? So that's the idea of our where we're gonna center our graph, and that's why we have an A inside here, because we don't always want to put the center at 0. If it's specifically at 0, then we have a Maclaurin then. So using this equation, we're gonna like do an example to see how this works. So let's use the example we've been working on. Y is equal to sine of x. Okay, so usually when I do this, I like to make a chart. So the first thing I have is n, and the second thing I have is the derivative. And the third thing I have is the coefficient. I'm just going to write c. And then the last thing we have is our final output, which I'm just going to put as FO. So let's rewrite our general equation, which is the summation from n is equal to 0 to infinity. And we have f of n of a divided by n factorial at x minus a is the power of n, right? So let's say we want to make make sine of x a polynomial, right? So we're doing a Taylor series on that. But we want to specifically have it center at 0. So at a is equal to 0, right? If it's centered at 0, is a is 0. If center is 1, then a is equal to 1. And if center at 2 is a is 2, right? Etc. etc. But if we want to center at a, but specifically we're going to write it center at 0, so a is equal to 0, this part, right? But as you notice, there's infinity over here. So the reason we have infinity is to account for like a bunch of polynomials, a bunch of terms. But we don't want to do that much, right? Because it's impossible to do infinite amount of terms. So to do this, we kind of like what we do in mathematics is that we get small sections. So let's say we want to do the first 4 terms. Okay. So we want to do the first 4 terms. So we start at n is equal to 0. So the first 4 terms is 0, 1, 2, oops, sorry. 1, 2, 3. Okay. So let's kind of begin. So when n is equal to 0, let's plug that into our equation. F of 0 is basically just our original function, so that's sine of x. And we notice that a, right, we had to put in a as equal to x. So a is 0. So sine of 0 is equal to 0, right? And then we have 0 divided by, right, n factorial. So n factorial, n is 0. So 0 divided by 0 factorial is 0, right? 0 factorial is just 1. 0 divided by 1 is just 0. So our final output, we take that 0 times x minus a. Our x is, we just keep the x. Our a is 0, and n is 0, right? So just follow the equation, right? So anything to the power of 0 is just 1, so 0 times 1 is just 0, right? So our first term out of our first 4 terms is 0. Okay, so now we have 1. So we have to do the first derivative now. So the first derivative of sine of x is cosine of x. Okay, so now we have to find cosine of 0 because x is now 0. We always have x is equal to 0 at this point because we center at 0. So cosine of 0 is 1. And now we have 1 divided by 1 factorial now is equal to 1. Now 1 times, sorry about that, 1 times x minus 0, right? Follow the formula. And then you put a 1 now because n is now equal to 1. So that's just x minus 0 is x, and 1 times x is just x. Okay. Now let's work on n is equal to 2. So the second derivative of sine of x, or is basically just going to be a negative sine of x. Or you just look at what we wrote here, right? So the derivative of sine is cosine. The derivative of cosine is negative sine, right? And you have to plug in 0 as x. So negative sine of 0 is just 0. So we put it 0 divided by 2 factorial is basically just 0. Now we have 0 times x minus 0, power of 2 now, right? So we take whatever's here and we put it as our coefficient in front here. So the reason I put a final output is that we keep track of where our terms are. So 0 times x to the power of 2, right? Because this is just x, then this is just 0. Okay, Now the third derivative of sine of x, so we just take the derivative of this negative sine of x, which is basically just negative cosine of x, right? And yet x is equal to 0 because the center is 0, right? So negative cosine of 0 is just negative 1. So negative 1 divided by 3 factorial is equal to negative 1 over 6. So negative 1, 6 times x minus 0 to the power of 3 is equal to negative 1, 6 x to the power of 3, right? So these are our first 4 terms. So that is 0 plus x plus 0 plus negative 1, 6 x to the power of 3. And that is basically the first 4 terms for a Taylor polynomial of sine of x. So sine of x in polynomial is basically just this. It's not really that precise because it's only the first 4 terms. If you add more and more terms, it'll make more sense. But as a caution, generally in math, 0 does not count as a term. So x will be the first term and negative 1, 6 x to the power 3 is the second term. But for this explanation, I'm just going to count these as terms so understand like how it kind of works out in the chart, right? So sine of x, which is what I described later on in the graph, right? We have x, and then we have even smaller, and x to the power 3. So that's how we like um, rewrite non-polynomials like sine of x into polynomials like this on the right side, which is just the general idea of the Taylor series using this formula. Now, the next thing we want to use with Taylor series is that since it's a series, we usually test for convergence. So how do we do this is that we use the general term and we use a ratio test. Okay, so let's kind of delete this and let's continue using this example. So what is the general term? Well, basically, if you kind of look at this graph, we have a, oops, we have a 0, 1, 0, negative 1, right? 0, 1, 0, negative 1, 6, right? We could, if you want, we could just find the general term for derivative and then general term for the coefficient. And then we general term of the derivative to get our general term of coefficient. And then use the general form of the coefficient to get the general term of our final output. But that's kind of like too much. And what we could do is that we could just find the general term of the final output, right? So let's see how that kind of works out. If we have 0, right, we have, remember our equation. Actually, let's kind of move back a bit. Let's kind of delete this section. So we still have our equation. Let's see how this works, right? Our infinity, we start at n is equal to 0, and we go to infinity, right? And we have the general equation. Now let's look at the pattern here. It's a 0, a x, a 0, and then negative 1, 6 x to the power 3, right? So the general idea is that if it's even, right, because when n is equal to 0 or 2, and if you add more terms, you're going to see the pattern also at 0, 2, 4, 6, 8, the final output is always going to be 0 if you keep testing it. I'm not going to because it's going to be a waste of time, but basically this is the final output. So when it's even, we're going to know that the output is 0. So instead of like calculating for that, well, let's just kind of like think about only for these, for the odds, okay? So we have x and then negative 1, 6 x to the power of 3. So let's kind of add like a fourth and fifth term so we can see how this actually plays out. Just gonna delete this, and I'll just add it later on. And cut. So we need a 4 and we need 5. So the derivative of cosine of x is negative sine of x. So negative sine of x times x. Sine of negative 1 is sine of x. And at sine of 0 is 0. 0 divided by 4 factorial is 0. So 0 times x minus 0 to the power of 4 is just 0. Now the derivative of sine is cosine. Cosine of x is equal to, when you plug in 0 here, that's a 1. So 1 divided by 5 factorial is 1 over 32. Or you could just put 1 over 5 factorial. It kind of doesn't matter. And then you put 1 over 32. Actually, is that actually 32? We have, oops, sorry, that is not 32. That is 120. Actually, I'm just going to put over 5 factorial. So it'll be easier to understand. 1 over 5 factorial. And then you have x minus 0 power of 5, which is equal to 1 over 5 factorial, x to the power of 5, right? So let's kind of look at this pattern. We have x, then we have negative 1 6 x cubed, and they have 1 over 5 x to the power of 5, right? So the general term for these, the general equation, how we write this, is that, let's kind of move this a little up so we have room. Okay, just remember that sine of x is basically we have a summation, and we could usually just start at 0 or the equation. It kind of doesn't matter. So we have, let's say x is, n is, since this is exponent 1, let's just kind of start at 1. And let's say infinity, right? 1 over, let's kind of edit that section. So 6 is just 3 factorial. So 3 factorial, right? And you could just have this as 1 over 1 factorial, which is just 1, right? Which makes sense as our coefficient is 1. So we went from positive to negative to positive, right? So let's kind of keep track of that. So we have negative 1. Positive is 1. And that when it's 1 is positive, when it's 3 is negative, when it's 5 is positive, right? So when you start at 1, it's going to be a positive. So we have 2x. And then if we add a 1, so usually how I test this is that I see how it works. So if x is equal to 1, that's 2, plus 1, that's a 3. Negative 1 to an odd is just a negative, which doesn't make sense because that's a positive. So I need to move this a little bit, right? So the reason I'm, actually, sorry, it's just x plus 1. Sorry about that, right? If you put a 1 here, that's a 2. Negative 1 to a 2 is positive. If you put a 1, if you put a 2 here, if you put a 2 here, then 2 plus 1, that's 3. That's going to be negative. You put 3 here, right? Because you're going from 1 to 3. Then you have to put a positive, negative, so it's alternating. So this is right. Sorry. And then you're going to have that as our 1. Now we have to keep track of the factorials. So when it's 1, it's 1 factorial. When it's 3, it's 3 factorial, right? So we have a 2x, oops, sorry about that. We have 1. So 2x minus 1 factorial, okay? Because if we have a 1 here, that's 2 minus 1, 1 factorial, which is what we started on. Now we need a 3 factorial. So you put a 2, 2 times 2 is 4, 4 minus 1 is 3, 3 factorial, right? Now if n is equal to 3, we have 2 times 3 is 6, 6 minus 1, that's 5 factorial. I know the n is not corresponding with this because the n is supposed to be 5 here, and I use it as 3. But generally, since n is technically standing for an amount of terms, this is also a general formula that kind of works. And now we just need to keep track of the powers, which is pretty easy because like the exponent is also equal to, is the same thing as our powers. So that's just times x to the power of 2x minus 1. Okay. So let's kind of like, sorry, I've been using x the entire time here. It's an n. So it's 2n minus 1 and 2n minus 1. Okay. So this is our general term. So the reason we found our general term is that we're going to use this for our convergence. So as usual with our convergence, let's copy and paste this, is that we like to we would like to use it to and the ratio test to find our like radius of convergence. So, okay, this was our equation. I'm just gonna rewrite it so it looks a little nicer. And we don't need the summation, so we could just have -1 n plus 1 over 2n plus 1 factorial times x 2n minus 1. Oh, sorry, plus 1. Actually, no, they're both minus 1. Sorry about that. And 2n minus 1 times x 2n minus 1. Okay, move this up so we get a little bit more room. Now the ratio test, as we covered on our previous videos, we have the next term divided by the previous term. So, or you could just have the next term multiplied by the reciprocal of the previous term. So we have -1. So we substitute n plus 1 to n. So now that's n plus 2 over n plus 1 here. So that's 2n plus 2 minus 1. So that's 2n plus 1 factorial, right? And then we multiply it by x over, and then you plug in n minus, it's basically the same thing as this. So it's 2n plus 1, right? Because n, you substitute n with n plus 1. And then you have this entire thing divided by um, this entire thing, which is the current term. So you have -1 n plus 1 over 2n minus 1 factorial times x 2n minus 1. Okay? And then we take the absolute value of that. We kind of have to move this over because I kind of forgot that you had to put a limit. Okay? And we have to find out when the limit as n approaches infinity. And that's just a ratio test. So what does this simplify to? Well, that's the limit as n approaches infinity, the absolute value. So then -1 n plus 2 divided by -1 n plus 1. It's basically just -1 on top, divided by. So we have 2n minus 1 factorial on top, because if you do the reciprocal, it's on top, divided by 2n plus 1 factorial on the bottom, right? This is the same thing. You can rewrite 2n plus 1 as the same thing as 2n plus 1 times 2n times 2n minus 1 factorial, right? This it's basically just minusing 1 every single time. So if you kind of cancel both of these terms out, we have 2n on the bottom, 2n plus 1 on the bottom, and 2n plus 1 and 2n. Okay, so let's kind of delete this. Okay, so we simplify that. Now we have 2x and x equals power of 2n plus 1 divided by x to the power of 2n minus 1, right? So this is just times x to the power of 2. Okay. If you don't understand how I simplify this, you might want to pause the video and like write it down yourself to see how you can simplify it. But this is the general equation, how it's right. Okay, so let's kind of move this up so we get a little bit more room. So as n approaches infinity, what does this simplify to? Well, the n is really big on the bottom. So as n approaches infinity, right? We know that as n approaches infinity, that since there is no term on top, and we have 2n plus 1 times 2n on the bottom, and n is the only variable. That means as this bottom part gets really, really big, nothing on the top will actually be like big enough to counteract this. So generally, the limit as n approaches infinity is 0. So we have the limit as n approaches infinity and n approaches 0. That means you get a 0, right? So the general idea for the radius convergence is that if the number is less than 1, then it's gonna, well, if the absolute value of that number, so absolute value of this is less than 1, then it's equal, then basically that's where it's gonna be converging, right? So let's kind of try like this is not for sine of x, but let's kind of try this for like, let's say we have the limit as n approaches infinity. And let's say instead of this, it's something like the absolute value is like 2n squared, right, on top, and then times the x squared, and then we divide it by 2n plus 1 times 2n, right? So let's kind of have this, right? Because I'm trying to show you how we had to do the first, if it's not exact, if it's the limit is not exactly 0. Because if it's exactly 0, that tells us that it's converging all the time. So let's see what happens when it's not converging all the time. How do we do that? Let's kind of move all this up. Oops. Cut. So as n approaches infinity, let's kind of simplify this, which is just 2n squared plus 2n, right? Actually, let's kind of erase this part. So, okay, so let's just have it as x. Okay. Oh, sorry, this is 4n squared, right? So 4n squared plus 2n. So we have 2n squared times x divided by 4n squared plus 2n on the bottom, right? And we take the absolute value of that. And we need to make sure that's less than 1. Okay? So as n approaches infinity, what does these numbers simplify to? Well, as it approaches infinity, our number just simplifies to the absolute value because you have 2n squared on the bottom and 4n squared on the, 2n squared on the top and 4n squared on the bottom. That just simplifies to 1/2, right? Which is the general idea of limits. And then we still have the x on top, so times the x. So 1 times x divided by 2 is less than 1. So you could say that it's just x divided by 2 is less than 1, absolute value of that. So then we know that x over 2 has between -1 and 1. So x has between -2 and 2, right? And that is where our interval of convergence is, from -2 to 2, right? But when we do this, we gotta test which ones work. Like always with the ratio test, as we explained in our previous video, we gotta test if this is gonna alternate, right? So let's say our original equation, this is just hypothetical, it's not correlating at all. Let's say our original equation was like -1, and then like uh let's say n plus 1 times x to the power of I don't know, n divided by, I don't know, n factorial something, right? So what we could say is if we plug in -2 here, then we have -2 to the power of n, which is the same thing as -1 to the power of n times 2 to the power of n. -1 to the power of n times -1 to n plus 1. That's just -1 to the power of 2n plus 1. And then you multiply by that 2n divided by n factorial. Sorry. So if we have 2n plus 1, 2n, if you plug in n as 1, that's an 2 plus 1, that's odd. If n is equal to 2, n times 2, that's a 4, plus 1, that's odd. If n is equal to 3, that's a 6, plus 1, that's an odd, right? So this is always going to be, this top part is always going to be an odd. So anything -1 raised to an odd number is always going to be -1, right? So this thing is not going to be alternating at all. So this doesn't make sense. So we can't have -2. But if we have 2 by itself, we have -1 n plus 1, and x is equal to 2 divided by n factorial, right? So it's always going to be alternating between negative and positive. So this is true because this is the alternating and convergence, right? So you have -2 is less than x is now less than or equal to 2. So you got to test the endpoints to know which one fits in the equation. So you always have to test it. But specifically for a sine of x, it's always going to converge. Okay, and that's the general idea for the second session, where you have to check for radius of convergence. I mean interval of convergence. And now finally, let's kind of use actually there's two more parts. So the next part we're gonna do is learn how to approximate like actual answers using a Taylor series. So instead of using sine of x, let's kind of now use y is e to the power of x. Okay, so let's say we want to find the first, I don't know, 4 terms, right? Usually the first 4 terms. And you want to center at 0. So 4 terms. So let's make a table again. We have n, our derivative, our our coefficient, sorry, that's a c, and our final output. Final output. Okay. Okay. So our first 4 terms is 0, 1, 2, and 3. So when we have e to the power 0, that's 1, right? 1 divided by 0 factorial, that's 1. And then you have 1 times x minus 0 to the power of 0, that's just 1, right? Now we have the derivative of e to the power of x is just e. And then e to the power 0 is 1. 1 divided by 1 factorial, that's 1. And then 1 times x minus 0 to the power of 1, that's just x. Okay, derivative of e of x, which is the second derivative of e of x, is just also e. The derivative of e is always e. So e to the power 0, because that's where our center of our graph is, that's 1. So 1 divided by 2 factorial, that's 1/2. So 1/2 times x minus 0 to the power 2, that's 1/2 x squared. Now if e to the power 3, the third derivative of e of x, that's also just e to the power x. So e to the power 0, that's equals 1. 1 divided by 3 factorial, 1 over 6. You might be seeing a pattern over here. And then you have 1 over 6. X minus 0 to the power 3 is equal to 1/6 x to the power 3, right? So once you master like how to do this, it gets really, really simple. It's just really tedious of how much we have to keep doing for the Taylor series, right? But specifically as a Maclaurin, because a is equal to 0, right? So our e of x is equal to 1 plus x plus 1/2 x squared plus 1/6 x cubed, right? So let's say we want to use this equation to approximate like e to the power of 1.1, right? So imagine if your calculator, right, did not have an exponent like e, right? And we can't raise to the power of 1.1. Using the Taylor series, we could be able to find out how to do this, right? Actually, let's say instead of 1.1, you want to find 0.1. So the reason I kind of changed it to 0.1 is that since we had center at 0, we had to put 0.1. But if you want to center at 1, we had to change all these numbers to 0. So instead of plugging in this number, we had to plug in 1, right? So I could try this explanation later on to show how this works. But let's just say we want to find e to the power 0.1. If you plug in e to the power 0.1 just on your calculator, you get somewhere around 1.1051709. Oops, sorry. 0918. Right? Somewhere around there. Now if we want to find x is 0.1, right? We just need to plug it into here. So 1 plus 0.1 plus 1/2 times 0.1 to the power of 2 plus 1/6 times 0.1 to the power of 3. And you get about 1.1051666666, etc., right? Which is really, really close. We have the 1 the same, the 1, 0, 5, 1. It's just right here that it starts to differ, but still really, really close. About like 5 significant figures really close, right? So that's really a really good approximation. And that's the general idea of why we could use it for why we use Taylor series, because we could use Taylor series as we could convert the non-polynomial into a polynomial, and then we could find exact values I mean not exact value, approximate values using the polynomial. So instead of like putting e to the power 0.1, if we don't know what it is, we could just plug in as a Taylor series and plug it into these really simple equations as polynomials and get really, really close answers. And that's the general idea of like how to use it with approximation. Let's try another example. Actually, let's try the exact same thing, but with another example. Delete. Let's say instead of finding e to the power 0.1, now you want to find e to the power of 1.1, right? So e to the power of 1.1. Oops, sorry. Right. So if we use e to the power 1.1, what is 1.1 closest to? Well, it's closest to 1, right? So now we can't center at 0. We need to center at 1 because that's what's it's closest to. So I'll put it up here so we kind of remember, right? Now let's make a chart. We have n, we have our derivative, we have our coefficient, and we have our final output. Okay, so we have 0, 1, 2, 3. So the derivative of e of x, as I always shown, is just e to the power of 0. The derivative of e of x is always just e of x, and then derivative of that is always that. So the first derivative, the second derivative, third derivative, etc., is always going to be e of x of e of x. So, right, we put in the center, which is 1 for all of them, right? I'm just simplifying it super fast because I'm just showing as an example. So don't worry too much if you can't do it this fast, right? So it's just e, 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 and e. Okay. Now c is our coefficient, right? Which is just e divided by 0 factorial, which is just e, because 0 factorial is just 1. E divided by 1 factorial, which is just e, because e divided by 1 is just e. E divided by 2 factorial, that's just e divided by 2. E divided by 3 factorial is equal to e divided by 6. Okay. So the final output is just e times x minus 0. Sorry, x minus 1, right? Because now we're centered at 1 to the power 0, which is just anything to the power 0 is just 1, so that's just e. Then you have e times x minus 1 to the power 1, so that's just e x minus 1. E times x minus 1 to the power 2, that's e x minus 1, 2. E times x minus 1 to the power 3, so that's just the same thing, e x minus 1 to the power of 3. Oops, sorry, that's e over 2, and that's e over 6, right? So our general equation, I'll put it back over here too. We have e plus e times x minus 1 plus e over 2 times x minus 1 to the power of 2, plus e over 6 times x minus 1 to the power of 3, right? So using our calculator, let's find out what's the exact answer e of 1.1 is. As approximation is 1.0041660 and 23, right? a bunch of significant figures, so we get a little bit more precise. Now, if we want to find using the Taylor series as a close approximation, x is equal to 1.1. So we could just plug in here. So e plus e of 1, e times 1, 1.1 minus 1 is just zero point 0.1, right? Plus e over 2, and then multiply that by 0 0.1 squared, plus e divided by 6 times 0 0.1 to the power of 3, right? And you get around 3.004154467, right? 3.0415. See, right here. Starting here, the numbers start to change. But imagine how precise it is. You are 5 significant figures really, really close. 3.041. That's how close we are to our actual answer. If you take the difference between these numbers, it's not even that much different, right? It's only a difference of about, oops, sorry, my tablet's kind of breaking. So that's a difference about that. These two numbers have a difference about 0.001155565. Look at how much of that difference is. It's barely that much. It's not even like 1%. It's about like a hundredths of a percent, right? So this is like if you use a Taylor series, while you're not going to get the exact answer, you're going to get a really, really close approximation. So and when I mean really close, I mean really close. And that is only when you have 4 terms. Imagine you add more and more terms. This difference would get even smaller. You get like a difference of 0.000000001, right? You could get really, really close answers. And that would be a really good number of why we could use a Taylor series to like represent like an actual number, because a Taylor series would get us really close approximations. And that's a really good practicality of using a Taylor series. Now, the final part of this video is that we're going to talk about is Lagrange's error bound, which is basically having um, a precise answer using our approximation, but now we're going to find like what error can it have from the actual answer. So remember we had that small error of difference of 0.00115 ish, etc. ish. So how do we know like how much of that error is there, right? And that's why we have this error bound. So what we could do is we have something called Lagrange's error bound. Okay, sorry about that. Lagrange's error bound, which basically states that if you have f of n plus 1 of z divided by n plus 1 factorial times a absolute value of x minus a to the power of n plus 1. So a z is just a number between your given number and your center. So in this case, it will be between 1 and 1.1, right? So z is going to be between 1 and 1.1. So the reason we have this here is because f of n plus 1 is basically you're just looking for the maximum number in that equation. So we have equation e of x. What is the maximum number of e of x if you only restrict it to 1 and 1.1? Well, exponential kind of looks like this, right? So if you go more to the right, so as the z increases, then the maximum number is what, 1.1. So the maximum number at this interval is just e 1.1, right? So all we have to do, oops, sorry, right? So all we have to do is just plug that in. So f of n plus 1 of that z is just e of 1.1. It just seems overly complicated to understand, but this is basically what it simplifies down to, right? It just finds the maximum number in that interval of that equation, right? N is your degrees. So we have a degree of 3. That's the highest degree we have, so use that one. So 3 plus 1 is 4 factorial times x, which is your 1.1, and then your center of rotation is 1. So 1.1 minus 1 is 0.1. So absolute value, actually, since this is already positive, I'm just going to leave it as 0.1. And then n plus 1. N is 3, right? So that's a 4. So using our calculator, we find out that our error bound is e to the power of 1.1 divided by 4 factorial, and then multiplied by 0.1 to the power of 4. So our error bound is 0.00000125, which makes sense, right? Because in our video, in a few seconds before I deleted it, we know that the actual difference was 0.00000115, right? Since the bound has to be greater than the area, it's greater than or equal to the area. I mean, not the area, the remainder, because this number has to be greater than this because we use the maximum number, right? So the maximum possibility of what the error could be. So we know that that answer has to be within 0.000125 of the actual answer, of the actual e to the power of 1.1. So using the Lagrange error bound, we can actually get a really, really close approximation. And I mean, using the Taylor series, we could get a really, really close approximation. And using Lagrange's error bound, we could find out like where our error of our number is within the actual answer. While we can't find the true exact answer, we know that our answer has to be really precise to some degree. And that's why we use Lagrange's error bound, which is basically just that simple. The max number divided by the degree plus 1, do the factorial of that and divide it, multiplied by the difference between the two numbers, which is 1.1 and 1, right? In this case, and not for all cases, it's just in this case, and then raise that to the power of the degrees plus 1. And that's just Lagrange's error bound. And that basically covers everything for Taylor and Maclaurin series. Thanks for watching, and I'll see you at the next math record.